metabolomics and exposomics, when we draw a blood sample, we think of it as a little microcosm of all the resources that all the cells in our body, both the bacterial cells as well as the human cells, need for growth and repair, as well as all their waste products. And we can analyze those, by a $500,000 machine here, a triple quadruple mass spectrometer for metabolomics. And for exposomics, we can look at environmental toxicants using gas chromatography, triple quadruple mass spectrometry. And the workflow is basically take a sample, add internal standards that are C13 or N15 or deuterated standards, run them through an HPLC, run them through the mass spec, isolate and fragment the ions, and then put them through a statistical analysis in order to come up with pathway changes that are reflective of the underlying biochemistry of the illness. So at UCSD, we have, so this is an illustration of the kinds of molecules that we interrogate by GCMS and LCMS on the exposomic side. So 1,232. And then we have on the endogenous side, 690 molecules that we interrogate from over 63 different biochemical pathways. So overall, that's 1,922 chemicals that we measure. So this is an example of the receiver operator characteristic curves for 10 different studies that we've done. Each one of these represents a $500,000 of research by 5 different people in our lab. And you can see that using metabolomics produces ROC curve accuracies of about 0.85 up to 1.0 in experimental models like C. elegans. But even in depression, where we're looking at cerebral spinal fluid or plasma, the accuracy of diagnosis is still very high. But what we found through these studies is that the actual prognostic value of metabolomics is even stronger than its diagnostic. So you have to imagine that when you take a blood sample from someone, you are really getting a snapshot of a moving train. Every person is on a train that is taking them to a particular location. We'd like that location to be, one of vibrant health, but people with chronic illness will be on a train that takes them into the future with multiple organ morbidities and typically exaggerated symptoms. So in this study of men and women with recurrent major depressive disorder, we took a sample at time 0, and then we followed them into the future and determined how long it took them before they had a recurrence of their depressive symptoms. And for women, it was about 600 days, and for men, it was about 300 days in this study. But when we use metabolomics to begin to see if we could predict which person would relapse and which would have sustained, absence of symptoms, we found that there were dozens of metabolites, and I'll give you just one, is methylcysteine. If we just stratified the patients into those who had the highest level of methylcysteine in the blue down here, and those that had the lowest levels of methylcysteine, it allowed us to tell so the median time to relapse was 400 days here in the orange for those who had low levels, and those who had high levels had actually over 850 days of symptom-free recovery. Same thing for males. We can do the same thing for males, with area under the curve for ROC curve accuracy that over 90%. We've also looked at, we're interested in newborn screening and autism. And so, we not only are doing work with newborn dried blood spots that are taken at the time of birth of every child in the United States, but we are also looking at the breast milk, because this is the chemistry of breast milk changes according to, well, just to start out, turns out that, we can take a sample of any breast milk and tell you whether that breast milk is being made for a baby girl or for a baby boy. So the milk chemistry changes according to the needs of the child. Okay, and so in this study, we took frozen breast milk samples at 3 different times, then followed the children for 3 years. And then went back in time, so we began looking at the children who had critical neurodevelopmental risks, and went back in time to their breast milk samples. And what we found is that with 8 biomarkers in the milk, we could identify with 91% accuracy the children, in this case 23 children at critical risk, with from 40 neurodevelopmental normal controls. Right. All right, so the last part of this is,
Can I interject there for 1 second?
Sure.
Yeah, I just wanted to ask you, to which extent you think this correlation, there's any form of causality, or it's just something that, because these kids have that problem, impact? What is your interpretation of this correlation? What is causing?
Well, so the information is actually in the details over on the left here. It turns out that cerebrosides, basically these lipids that are of critical importance for developing brains, are fortified in the milk of mothers who have children who are struggling neurodevelopmentally. So however the biological connection is made between mother and child, through smell and sight and scent and touch, the mother's milk is fortified with, basically these dihexacylceramides, and a variety of different phospholipids, monohexacylceramides. These are glycosphingolipids that are cerebrosides that are necessary for brain development of a child. So the mother whose child is struggling the most makes the most.
Mm-hmm. So you will predict that a lack of those cerebrosides would actually directly, potentially be causative of the disorder?
No, I don't think of it that way. I always think of everything as a reactionism. Okay, so
it's an expression of the change in the homeostasis, if you wish, or anything like that.
Yeah. So so I always see this, as the body's response to a problem. Okay. And so the interesting thing is that the milk for neurodevelopmentally normal children had lower levels of these molecules. Just meaning that normal kids, that on a normal course, don't need as much cerebrosides in order to have a normal brain. But the kids that are having problems, are helped by, this maternal child chemical bond.
Thank you.
Okay. So this is a big data question. Basically, if the number of samples N is much less than the number of parameters measured, then you can run into problems that frequently are, not obvious. So we performed a little simulation study where we used a random number generator to populate a matrix of 691 metabolites in 60 patient samples, so 30 cases, and then just basically just randomly divided those 60 samples into 2, so controls and cases. And lo and behold, when we use multivariate statistical analysis, so basically whether you use PCA or partially square-screwed analysis, you get similar results. Basically, you can always find metabolites that are discriminating between the 2 groups. I've named them ASD and TD here, but really they're just, cases and controls. But the thing that there's already there's a caveat here for anybody who knows metabolism, is that these metabolites come from many different pathways that they're randomly selected from different pathways, okay? There's not an intensification or hierarchical structure to these results. And if we just re-randomize the same data set, we get a completely different set of metabolites. And if we look at, let's say we thought that first was going to be a discovery set and that second one might be a validation set from a different, clinical study, one study might be done in Philadelphia, another might be done in San Diego. When you look at this, lo and behold, you get 12 metabolites that are shared by these, two, and remember, these are random data sets, okay? And in the literature, a lot of people would say, okay, that's what's shared. That's what's important, is these 12 things, okay? Well, wrong. Now I'm going to give you a kind of a quick trick that we use in order to tell the difference between strong studies and weak studies. If you just take, let's say we have 691 metabolites, and we can take the p-values, and that can be, a non-parametric p-value would be a Mann-Whitney U-test p-value, and then you could use a student's t or a Welch's which is what you would choose if the distribution is still symmetric, but the variances are different between the groups. But anyway, if you take all those p-values and you just do a histogram, frequency histogram, you'll see it's roughly equivalent, from the lowest values to the highest values. And in fact, what's interesting is that it comes up, so Q is just a Bayesian false discovery rate. If you take 0.05 times the number of metabolites, you get about 35, which is the average of all these little columns, bars, okay? So this is a weak study that is generated from random data. It's very easy to do too. I mean, this is a very easy thing to rapidly assess the quality of data from big data sets. Now, here's an example of a couple strong metabolomic studies. So here's a mouse study. Turns out it was only 15 animals, 7 controls, and 8, animals that happened to be injected with ATP. But you can see that there is a very strong, increase toward the low p-values. Okay? And in a human study, you can see also that there's a very strong increase toward the low p-values. Okay? This is really very dramatic and easy to do to rapidly assess the quality of any big data set.
Is that a description of all pairwise interactions that you could have within the data set, every interaction among all of the 691 or whatever the case may be?
It's related, but that gets into Pearson and Spearman matrices. So it turns out you can also determine p-values for every pairwise analysis in a Pearson matrix or a Spearman matrix, and do exactly the same thing, and you'll get the same results. So it's very, very useful, quick test. Okay. So now if you do a random, we like random forest because it's very robust or resistant to overfitting your model. And in this example, which was generated from a random data set, the out-of-the-box error was 0.6, and we like to see out-of-the-box errors of below 0.25. Okay, I won't go through a lot of this. This is just another example. Again, this particular out-of-the-box error was again 0.6, and this is again we want to be below 0.25. So now, if you have a strong data set, this is what you get. So the out-of-the-box error, the misclassification, was 0. So in these animals, okay, and in this particular one, which is another strong data set from major depressive disorder, it was 0.17. So again, below our 0.25, optimal threshold. You can do, heat maps, and you can make yourself believe that, some random data set is going to be different, between cases and controls. But, this is what on the right is what a real, strong data set heat map looks like, okay? With metabolites that are strongly increased and strongly decreased by treatment versus control. So that's it. And I'll take questions. So I was 2 minutes over, but